Welcome everyone to the fifth lesson in chemistry. Today we'll be looking at the four quantum numbers. So we can see here that there's four letters. Each one of these letters represents a specific attribute of an atom in the way that it's kind of arranged. So we're going to be starting with N here. So N on the far left is known as our principal quantum number. Now N is basically just the energy level or the shell of electrons. So I'm just going to write E for energy level, or shell of electrons. And then basically it has values that are typically natural numbers. So your numbers like 1, 2, 3, 4. Because if we think about an atom, I'll just draw it over here, right? We can have energy level 1, 2, 3. We don't have like an energy level like right in the middle here, right? We'll have an electron here, there, and there, right? So those N's basically just represent the lines in which we find electrons. So it has, so you can just say N is an element of natural numbers, like 1, 2, 3, 4. And then basically a higher N value means a higher energy level, which means something's farther from the nucleus. Because if imagine, here's our nucleus, 1, 2, 3, 4, 5. Let's say we have an electrons all the way here on the fifth energy level. That's a lot farther than something that's like right here. We're comparing a distance like this versus just that, right? So the further away something is from the nucleus corresponds with the higher N value you have. Now, moving on, we have the L value. So what L represents is L is the angular momentum quantum number. What's special about L is that L corresponds with a specific shape of the orbital, or the subshell. So I'm just going to write shape of subshell. And the key word there is the word orbital. So I'm going to write that in quotations, orbital. I'll get into defining what orbital is later, but just have that note at the back of your head that this is very important into what we're doing right now. So values of L can be from L equals 0 to L equals N minus 1. So basically whatever N is, remember how we had the diagram with like the fifth energy level? Well, if in that case, L can be from anywhere from 0 to, what's 5 minus 1? 4, right? So the L can be from 0, 1, 2, 3, 4, pretty much. And the different numbered values kind of just relates to a different orientation of your orbitals, which I will get into in a second. Our next quantum number is M with a subscript of L, which corresponds to the magnetic quantum number. Now, the meaning of our ML is it kind of just relates back into what we said about orbitals. And rather than being the certain shape of the orbital, this time we're branching off of the shape and we're looking at the orientation of the orbital. Because these specific shapes that we've talked about before, they can go on the X, Y, or Z axis. They can be in all sorts of different regions in space. M subscript L, or the magnetic quantum number, kind of just tells you which one we're looking at in this case. Because what we're doing with these four quantum numbers is kind of like identifying like a certain electron, you know, or like where to find an electron based off of our last video with the wave-particle duality. Now, its values can range from negative L to positive L. So for example, let's say we have N is equal to 5. Well, if N was equal to 5, L could be from 0 to 4. Let's say, and then if L was 4, then our different orientations can be negative 4, negative 3, negative 2, negative 1, all the way up to positive 4. Shape of the subshell corresponds to the specific orientation of the subshell. It's just a further down description of what you're looking at within an atom. Lastly, we have M subscript S, which is the newest one, or the spin quantum number. Now the spin quantum number basically just says the spin of an electron. So this goes into a lot of specific theories in string theory or other fields of science, but really all we gotta know right now is just that electrons with their charges and stuff can be attributed to the specific spin that they have. So spin of electron. And its values range from plus 1 over 2 to minus 1 over 2. So these values, that's it. It doesn't relate to the past N, L, or ML. It's just plus 1 over 2 to negative 1 over 2. That's pretty much it. Now, the interpretation of this is kind of just that two electrons can occupy the same orbital as we mentioned before if they have opposite spins. So I'll just write that as a note. So opposite spins, so meaning like positive or negative, can reside in same orbital. Now, so what is this orbital thing I've been talking about? So as you know, around a nucleus, there's orbits, right? And these orbits have electrons. But as we talked about in the last video, it doesn't really work like this. There's not really specific regions and lines like orbits of planets around the solar system in which we can find electrons. Instead, thanks to Heisenberg's uncertainty principle, we don't really know where the position or what the position and momentum of an electron is. So instead, we use these hypothetical measurements of orbitals. So what are orbitals? Orbitals are regions in space where electrons are likely to be found. So since we talked about in the last video that you can never really know where an electron is or like what its momentum is, we have to do our best to assume where it is. So I'll give an example. Let's say it's a Monday morning and it's 10 a.m., right? If your parents don't know where you are, they don't know where you are specifically, but they can look at context clues and say, okay, well, it's a Monday morning and it's 10 a.m., okay, then my kid should be at school. So that means that in this case, school would be the orbital. School is the region in space where you as a student are most likely to be found. So we look at these orbitals in 4 different shapes. We have S, P, D, F. These don't mean anything specifically, like they don't stand for anything, but they just correspond with different shapes, which I will get into. So in this figure that I found online, it pretty much accurately shows how the SPDF orbitals kind of like work. So basically, you might be thinking, okay, this just looks like a periodic table with just spread into like 4 different blocks, which yes, it is, but we can think about it as being each atom that resides in one of these blocks will correspond with that kind of shape. So let's give an example, right? Hydrogen will be right here. We can add a little line. We can say this would be hydrogen number 1, right? And then let's just add helium for reference. So we'll add helium. Helium with number 2, right? We can add anything. So we could have like, in the P block, we could have like 16, and here we could have like oxygen, right? So all of the elements on the periodic table are within this diagram, right? It just doesn't show it because you don't really need to know it. You just need to know the placement of it, and then you could say, okay, oxygen's over here, must be in the P block, right? So this is basically just saying that in an atom, it's going to have its final electron, like its most valent electron, inside of this certain orbital. So let's say, for example, our hydrogen, right? Hydrogen is in the S block, which means that when we look at hydrogen, and hydrogen has its 1 orbital, so we have H, then we have the 1 orbital around, right? E minus. That means that this orbital is going to be found in the S block because it is in the S block of the periodic table. Or let's just take oxygen, for example. So we had oxygen down here, right? O16, and then we know that oxygen is in the P block. So it means that oxygen can have its all different arrangements. It can have an arrangement of P or S orbitals, P orbitals, but it's going to have its final electron, because it has 2 and then 6, or 2, then 8, and then 6 on the 3rd energy level, that on this 3rd energy level, it's going to occupy the greatest orbital of a P orbital, or a P block, putting it in its place over here. So this is just a pretty helpful kind of visual aid to show you what we mean by SPDF orbitals. So like I said, SPDF doesn't really stand for anything. It's just a way of signifying what shape we're looking at. So you can see here, S, right? These are all kind of like 3D shapes, but our S shape here is like a sphere, right? So you can imagine it like a sphere, right? So that means that within this sphere, there can be orbital here, orbital here, orbital here, orbital here, right? It's just that within this sphere, it's a very high likelihood of finding it. That's why it's called an orbital. And then moving down, we have P's. So we have P orbitals. So this was just a sphere. This one is a bit different. It's kind of like these two lobe kind of shapes, if I can draw it like that. So it means that within these lobes, there is high likelihood of finding electrons. See, look, this is what I meant though, where I said that the ML and MS are used to signify what type of shape we're looking at. Because although we have the letters to signify whether it's a sphere, whether it's these 2 shapes, 4 shapes, or whatever, we still need the orientation, which is where ML comes in. So see, look, we have P -1, P0, and P1. What's the difference between these two, or these three? Well, we look at the axis. We have a Z, Y, and X. On P -1, they lie on the x-axis. So there's one right here, and there's one right here. And then we can see the x-axis cuts right through them. Then this one, they're on the z-axis at P0. So this is the p orbital, and then like this right under it. And now this one, they lie on the y-axis, right? They're parallel to it, just like that. And now moving down, we get a bit more complicated. So these are the d orbitals. These are my personal favorite because they're just really complicated. But we kind of have these 4 Easter egg type shapes, right? They're like ellipses, but in 3D. So we can see that here, we'll look at D1 first. So in D1, we have this shape right here. We have another one underneath, one right here, and right here. And all these are just these 3-dimensional regions in which you are very likely to find an electron. And then just like before, the reason why we have different numbers is because they're parallel to certain axes. Now this middle one is where we get into a little bit of complication, because you might be thinking, okay, so we have 4 orbitals here, 4 here, 4, 4, 4, 4, 4, 4, but then suddenly, why do we have 3? And why is this one like shining? Well, this is a little bit different. What this actually looks like is that there's kind of like this donut-shaped ring. I'll try my best to draw it. I know you all know what donuts look like. So here we have a donut, and then underneath we have this big region, and then above we have another big region. That's pretty much what it looks like. So we have region here, and then this donut kind of shape all around coming at the back. So, and then within any of those shapes, the donut, the top lobe, the bottom lobe, you're very likely to find an electron. Because, like we said, orbitals are just these hypothetical spots in which you should find one. And then f orbitals are very, very complicated. They're like the ones before, but see, this one has like 2 donuts on it. I think you kind of get the gist from here, from the SP and D. You can kind of assume what the F are going to look like. Just remember that there's these 3D regions in which you're very likely to find an electron. Now, this is the second diagram, which I personally love. I use it. I think I write it on every single test. It's basically called the Aufbau diagram. Now, what the Aufbau diagram does is it kind of just shows our N, our L, our ML, right? It just kind of shows our quantum numbers and how they relate to the different sub-level types with SPDF. So just like how we had on the periodic table shown before, we have we have S, we have P, we have D, and we have F, right? So we can imagine that there's a separate kind of category here going S, P, D, F, and then along the side we have 1, 2, 3, 4, 5, 6, 7. Now, if we remember back to our quantum numbers, what was the first one? The first one was N, and N was the principal quantum number. So the principal quantum number just kind of dictated which energy level we were on, because remember we had like our example with oxygen, we had the first ring, second ring, third ring. So, but these are also just energy levels. So we have energy level 1, energy level 2, energy level 3. So if N is 3, we're on this one. Right, so that's kind of just a little refresher on what our N's are. So in this case, we are looking at it as to say that N is going to be the first digit or first character that comes up in each of these little units here. So if we have one S, right, that means that we're looking at an S orbital. So look back to the diagram we had just had, and we remember that S is kind of like a sphere, right? Which means that if you're going to find an electron, right, that's going to be 1s, you're going to look on the first energy level, and you're going to look, and it's going to be somewhere inside of the spheric region, right? That's 1s. Now, 2s would basically just be saying, yes, we're still looking for the sphere, we're still looking for that shape, but we're going to be looking on the second energy level, which means we're going to be further out, because here we have like this is like our 1s, and then our 2s would be further out, 3s, 4s, right? Just because energy levels get bigger, right? A higher energy level means the further your electrons are going to be from the nucleus. And then that pattern continues all the way down here to like all the way down to 7s. And then we can say, okay, we understand the s column. Now onto the p. So the p column, pretty similar. It's just that we have our p orbitals, which I'll just go into them. We have the first one like this, the second one like this, and the third one like this, right? Each on the different axis. So basically what we're saying here is just that that on the second energy level, right, our electrons are going to be not found in the spheric region, but that these certain electrons are going to be found on the p region, so in these little lobe areas, like here. And remember, we have 3 because it's on 3 different axes with the ml quantum number. Now, you might notice something here. Why is there no p orbital for 1? Well, it's because in the first energy level, you can't hold a p orbital. Remember, the first energy level can only hold 2 electrons, right? So if we look at helium, helium's a noble gas, right? It's stable. So on helium, we have 1 and we have 2. We have 2 electrons, right? This is like a full octet, right? This is a full energy level. So basically so helium has its sphere of electrons, right? And there's 2 inside of here. That's it. It doesn't have any more, doesn't need any more orbitals to hold its electrons, right? It has its storage just in the one sphere. So it wouldn't make sense for something to have in the first energy level, such as hydrogen or helium, to need any p orbitals, because if they only have 1 or 2 electrons, right, they can just hold those in the sphere. So that's why we actually have this little 2 here. So going to the little third character here, the 2 dictates how many electrons you have in the specific orbital type. So, for example, 1s2, this is basically just saying we have helium. Because when you look at it, right, where are our electrons? They're in, so let's say we have an atom here, and we have energy level 1, right? So this is where the 1 comes from. Our n is 1. But then our s is saying that this region here is really just a sphere. And within this sphere, how many electrons are there? Well, let's look at the number, 2. 1 and 2. What atom has 2 electrons? Helium. So basically just saying that this specific configuration of 1s2 is another way of writing helium. So you may see on certain periodic tables that like on helium, you would have helium, number 2, and then you'd have the mass, and then underneath you may have 1s2. Depends on what you have, but if you have that, that's basically just saying that that's the way of writing out what helium is through electron configuration. Now the same applies to the number 6 here, or the number 10 here, because as you remember, there's more lobes and more regions of finding electrons when we go from S to P to D to F, which means that naturally there's going to be higher numbers. If the max we can have here is 2, the same can be said here for the p orbitals, in which they have a 6. So like we said before, 2 is the max we can have for the s orbitals, while 6 is the max we can have for the p orbitals, which is why the max we will have here is 6. Now, you know what? Let's do this. Let's go to 2p6, and let's try to identify which atom this is, right? So we know that we're going to have an atom here, and we're going to have first energy level, which we don't really care about, and what our second energy level is what we really care about, because we have a 2 out in front. That's that circle, like this. So we have our second, we're going to look at the second period on your periodic table, right? So if we look at our periodic table, the first period with hydrogen and helium, we can cross those out. We're going to be looking at the second one, right? And then we can ignore lithium and beryllium because those are in the S block, as we mentioned before. So what are we going to look at? We're going to look at the P block now. So moving over to the P block, then we can say, okay, we're going to have 6 orbitals in this P. So we're going to have one sphere of our 1s2 that's going to have 2 electrons in it. A second sphere of our 2s2, which has another 4 electrons in it. So now we're at 4 electrons, and we haven't even touched a p orbital yet, right? But we have 4, but we still have leftover electrons. So what are we going to do with those? Well, we have to put them somewhere. Let's put them in a p orbital. So now we get a p orbital, and then we have how many in it? We have 6. So we had 4 electrons before, plus another 6 electrons. That makes 10 electrons. Which atom has 10 electrons? Neon. So it means that this, 2p6, is really just neon. Now, a little quick way that I like to remember it is basically just saying that if you know that P can hold a max of 6 and S can hold a max of 2, that if you see a 2 on an S or a 6 on a P, right, ending off an electron configuration, you know it's noble. It's a noble gas. You know that is the subshell, and that is the max amount that it can have. It can't have any more electrons. It is a full subshell, which means it'll be a noble gas. It'll be stable. This pattern also extends to 3d10, for example, because as SPDF continues, there can hold more electrons. 4F, and like from before, 1, 2, 3, 4 is just basically which energy level you're on from 1, 2, 3, 4. Then it's going to hold 14. And the reason, though, why we have this diagram is because we need to remember in what order do we write something. So let's go back to our example with neon, right? Neon, although it was just 2p6, it had preluding electrons, right? It's not just 6 electrons. If it had 6 electrons, it's carbon, but it's not, right? It's neon, and that's 10. So where did those other electrons go? So we know that it's going to end in 2p6, right? A, because p6, max noble gas, like I just mentioned, but B, because, well, we did the math, right? We saw that, okay, it was a second energy level, p orbital with a max amount. That must be neon. But this is the thing. If we only have 6 electrons here, we need 10. So what we can do is we can say, okay, well, every atom from hydrogen is going to start with having s orbitals. So we're going to go 1s, and then is neon going to be missing any from that first octet? From the first kind of like orbital of electrons? No, it's going to fill it in order to go to the next one. Because if this wasn't full, we wouldn't be able to get to this. So it means that this is going to be filled here, and then what comes after 1s? Well, let's use the Aufbau diagram. So we look at these arrows and to where our eyes are going. So first we go, bang, this way. We go 1s2, we got that. Next, where the second spot our eyes are going, boom, 2s2. So it means that after 1s must come 2s. And then, like we mentioned before, this must be filled in order to get to this. So this must be 2s2. And if we add up all of our powers here, we have 2 electrons, 6 electrons to make 10. Again, 10 electrons relates to neon. So the Aufbau diagram is really just shown to tell us where we need to look in order to write our electron configurations correctly. Because if we were to keep going, if we were to get an atom that was further on the periodic table than neon, we would just keep looking at the diagram. Let's say we got one in the D block. Let's say we just got a multivalent metal in the D block, right? If we were writing the full electron configuration, like with any atom, we start with 1s, then go to 2s, then go to 2p, then go to 3s, then go to 3p, then go to 4s. And then this is where it gets a bit tricky, why we need the Aufbau diagram, because sometimes you would think, okay, so I go from 1 SPDF, 2 SPDF, 3 SPDF, 4 SPDF, but sometimes with the way that electrons overlap and they get further from the nucleus based off of the way orbitals are built, you will have specific energy level types that are further away from the nucleus than others. So for example, when we look at it, that's why we have to look at it at this angle, because what we're saying here is that the 4s2 comes before 3d10 because of the arrangement of the orbitals. So we need to take that into account, and that's why we need these little arrows here. So it means that, let's say we have an atom that's 7p6, right? If we were to write this, another way of writing it is by going 1s2, 2s2, 2p6, 3s2, 3p6, and then continuing all the way on, writing all of these out all the way until we get to 7p6. Now there are shorter ways to write this in which we can shorten it. We can kind of combine the coefficients and the energy levels. We can say 1s2 and then 2s2, but instead of rewriting the 2, we can go p6, letting us know it's still with that coefficient, but now it's under the 2, right? Since there's no 2 with D, we can go 3s2, keep looking here, 3s, then after 3s2, we have, well, let's just look here. We have 3s, and then we have 3p. 3, P6, but remember we don't need to write the 3, so we can just write P6, and you can continue that all the way until you can get to 7P6. But remember, when you are going to switch between energy levels, you do need to rewrite the coefficients. So for example, you can have 3s2p6, and then say, okay, after this I need 4s2, so you can go 4s2. But then if you're going to write that 3d10, you do need to rewrite the 3, just to let people know that you're not jumping from a 4s orbital to a 4d orbital out of the blue. You just need to remind your viewers or your teachers when you're writing a test which energy level you're talking about, and which shell you're talking about, and how many electrons there are in that orbital.